Our next speaker is Ramandeep Johal. He'll be talking about microscopic Legendre transformation and canonical ensemble.
First of all, I would like to thank the organizers for giving me the opportunity to present my talk. I also congratulate the organizers on hosting this meeting for 10 successive years. So, thank you very much. So today I'm going to talk about the microscopic version of the Legendre transform and then apply it to canonical ensemble. So this version of the Legendre transform is slightly a non-standard treatment of this technique, and I'll explain that. So this is the overview of my talk. So first we have to kind of talk about the standard transform. So the Legendre transform is a tool or mathematical technique which switches from one set of variables to another. And you may like to do so for various reasons. It may be more convenient choice of variables and so on. So it's a very useful technique which is used in physics, also in mechanics when we go from Lagrangian to a Hamiltonian formulation, or as in thermodynamics or statistical mechanics, we want to change the variables from, say, energy or entropy to temperature and so on. So mathematically, it's actually called the Legendre differential transform, in which there is an optimization involved. So this transform of this function is defined in this manner. However, in physics, it's usually called the Legendre transform only, because Legendre only studied this formulation, in which actually for a given p, you want to find the value of this function when the derivative of this function has the value p. So we'll explain that. For example, you are given the fundamental equation of energy in terms of entropy and volume. You define the temperature like this. And then Helmholtz free energy is an alternative choice of the thermodynamic potential, in which the independent variables go from S to T, right? So here S is the independent variable, but it is being replaced by the derivative of that function. Similarly, you can define the Legendre transform of entropy. This is slightly redefinition of the variables in which beta is now the inverse temperature. So beta F is the Legendre transform of entropy, and similarly you can define the inverse transform. Now we go to the canonical ensemble, in which the system is in thermal equilibrium with the heat reservoir, and its equilibrium distribution is given by this. There we define equilibrium free energy. By this definition, you define the mean energy as the derivative of the free energy, which gives you the natural definition of a mean energy, and then entropy is given as a Legendre transform of this function, free energy. When you substitute the equilibrium distribution, you see that the entropy function is given in this form. So this is what Shannon entropy looks like. So this is also called the Gibbs entropy. So Gibbs entropy at equilibrium is equal to the Shannon entropy. Of course, Shannon entropy has no dimensions, and Gibbs entropy has the dimension of the Boltzmann constant. But here we have absorbed the Boltzmann constant into the definition of beta. So beta is like 1 over kBt. Now, there are many ways to derive the canonical distribution, and one of the alternative ways is the Jain's principle. So Jain's principle of maximum entropy says that if you are given a set of constraints, which are in the form of mean values, so the mean value is constrained to have this value, then the most unbiased estimate of a probability distribution is the one that maximizes the Shannon entropy. So Jain's was inspired by this observation that at equilibrium, the entropy is actually given by the Shannon form of the entropy. And so he said that if you maximize this function subject to these constraints, then you arrive at the most unbiased estimate of the distribution. So the method to do that is the method of Lagrange multiplier. You want to incorporate certain constraints by introducing these parameters, and you want to optimize this function. So when you do the variation, then you can show that the distribution you obtain is the canonical distribution. So these Lagrange multipliers, they are to be determined by the imposed constraints. They have to satisfy them. So you can incorporate as many constraints as you like, but they are all of this form. So you can formulate different ensembles in this framework, and then you get the standard canonical exponential family of distributions. So after doing that, then you can define the free energy analogs and so on, and you can say that the maximum value of the entropy, which you are optimizing, is may be given in terms of a Legendre transform kind of structure, in which you go from a function which is of these Lagrange multipliers to a function which is of the values of those mean values of those variables. So again, if you apply it to the canonical ensemble, then there is only one additional constraint on the mean energy. And when you do the variation of that function, you get this is the variational condition. Now here the logic is that because you can vary all the probabilities as independently, then this equation can hold only if each coefficient vanishes. So each coefficient for each I has to vanish, and then that gives you the distribution. So after obtaining the distribution, you say that now it satisfies the Legendre transform structure in which you transform from the independent variable as beta to the variable as u. So this is the standard approach in which we have seen that the canonical or the Gibbs entropy is equivalent to Shannon entropy at equilibrium. Also, equilibrium free energy is related to thermodynamic entropy via the Legendre transform. So according to Jain's, the thermodynamic entropy may be related to the Shannon entropy. In fact, he thought that they are the same concept. So now the question is, one may ask that, can the equilibrium free energy be directly related to Shannon entropy via an optimization procedure? This is what I define as the microscopic Legendre transform. So this is the standard transform you do. There is a minimization of the over the energy for a given beta, and then you get a free energy function like this. So now here we focus on this combination of quantities, and because in the canonical ensemble you want to define mean energy like this, so beta u I rewrite like this. So I introduce a function in this form in which I want to go from a function of probabilities to a function of another set of variables. Right? So this is the definition of the Legendre transform of some function which is a function of the probabilities. Okay. So now, but the entropy has to involve independent set of variables. To do that, I have to incorporate the constraint of normalization, right? And then, so the optimum condition when you do the minimization would be this, right? So now this actually allows you to introduce the exact differential of Shannon entropy, which will be defined like this, because now you can vary all the probabilities independently, right? So from this definition, you can write this, but at the optimal point, we have seen that it should satisfy this condition. So when you combine both of these conditions, you get the equilibrium distribution. So this is the way. Then similarly, you can define the heat in this procedure, where actually heat is defined by this. When you keep the volume fixed, then heat is given by this. And then when you impose the Legendre transform condition here, you get the definition of the heat. So here you see that beta can be interpreted as the inverse temperature, because this is change in entropy, this is heat, so this will be the inverse temperature. So finally, I would like to emphasize that the Jain's approach can also be looked upon as equivalent to this approach, because when you consider the system to be in equilibrium with the reservoir, then the total entropy should not change. It is a reversible process. Now ds is given by this for the system, and if heat is defined like this, then for the reservoir, you can impose this condition, because if you interpret now beta is the inverse temperature of the reservoir, then heat exchange is same and opposite sign. Then if you combine this with this, you get this condition, which is exactly the same variational condition as obtained by Jain's. So now here the probabilities can vary independently because of this condition. It's an exact differential, and so each term should be 0. So this also gives you the canonical distribution once again. So just to conclude, microscopic transform gives you an alternative perspective on the derivation of canonical ensemble and also similar other ensembles. And future application may include applying to non-equilibrium processes or working with more generalized entropies. So this was published here. Thanks for your attention.